Hello everyone and welcome to the substructure component of Structure 2. In this part of the course we'll be learning some basic geotechnical concept, and this video is about what is soil and how it is formed. Now let's start with a question. Why we're learning about geotechnical engineering? Now if we look around, you'll see all the structures around us are usually founded by ground. Now if we want to build something on top, make it economic, make it risk-free, we have to have some basic understanding of the behavior of soil, because the load carrying capacity of the soil basically depends on its mechanical properties. Now, we all are convinced we have to learn about geotechnical engineering. Now let's see what is soil. Now, different group of people, let's say an agricultural person or a geologist, may have different definition for what is soil, but to an engineer, soil is a mixture of soil solid particles with gases or liquids in its voids, basically on top of which we build all the different types of structures. Now, under a microscope, a soil might look like this. These gray bits, they are soil solids, the blue bits are water, and then the white bits are some gaseous, basically air. And we call it three-phase material, basically the solid, water, and air, the three different phases of this material. And it is generated from disintegration of different types of rocks. Now, to understand a bit more about soil behaviors, we often convert this figure on the left to something like the figure on the right. We call it soil phase diagram. So what we have done in this figure is we have taken all the soil solids and lumped it into one mass. That's water lumped into one mass, and all the air in one mass. Now from this diagram we'll be constructing a number of definitions that will help us understand the soil's behavior a bit better. Now same diagram as before. In this diagram we have solid, water, and air. This M and V terms on the right hand side, M stands for mass and V stands for volume, and A, W, and S stands for air, water, and solid respectively. Now if we add all the V terms, we'll get the total volume. If we add all the M terms, we'll get the total mass. Now we're going to define a term for density. We call it bulk density. If you look at the definition closely, you'll see this definition is not very different from the regular density definition you have learned. Now in soil mechanics, bulk density is not a very good representation of soil's behavior. We use another term called dry density. Why dry density and how it better represents soil behavior? Let's draw a picture. Let's say this is a soil element with a number of particles in it. Let's assume we have magnified the soil thousands of times. And then if we apply some loads on top, what will happen? The soil will deform under the action of this load. Now, how the soil is carrying or resisting to these loads? Basically, the soil is transmitting these loads through these interparticle contacts. Now let's draw another soil. Now let's draw it slightly differently. Now the difference between this soil and the soil in the previous picture, let's call it A and let's call it B. Let's apply the same load. Can you spot the difference? Soil B, even though they have pretty much the same volume, soil B has much higher number of particles. Higher number of particles basically means the soil will have higher value of MS. That means it will have a higher dry density. Now if we look at the behavior of these two soil A and B under, let's say, same amount of load, which one do you think will deform more? Obviously, answer is A. The B will be a bit stronger. Why? See, there are a number of small particles within this soil matrix. That basically means the number of contact points are much higher. That means the interparticle friction generating from those contact points are much higher. And another difference between A and B is, see, there are lots of void space in picture A, and then all the particles can rearrange, have a bit higher degree of freedom for the particles to move, so they can rearrange quickly, easily. So this will deform more. On the contrary, B, since it has all the voids filled with smaller particles, the particles has less degree of freedom to move around. So that will be a bit stronger while responding to the external load. Another definition I'll talk about here is water content. Water content is the ratio of the water in the soil to the amount of solid in the soil. Now, this definition has some strange implication. In some cases, the water content, we use the simple W, can be more than 1 or 100%. Just think about it. I won't explain it any further. Think about it and look at the definition. You'll understand why. Some typical numbers for density terms: water 1000 kilogram per meter cube, clay 1500 to 1900 kilogram per meter cube, sand 1700 to 2100. You have the numbers for gravel and concrete as well. Just to give you a sense of what the density term number for density term might be. Anyway, now let's go to the second stage. We have learned what is soil. Now in the second stage, we are going to learn what is or how the soil is formed. Basically, as I have mentioned earlier, all the soils are formed from disintegration of rocks. At the beginning of time, or at the beginning of Earth's history, everything was molten magma, and then those magma became cooled and solidified, became igneous rocks. Some of the igneous rock became metamorphic and sedimentary rock. That's a different story. But basically, because of a process called weathering, these different types of rock broke down into smaller particles and created lots of sediments. That is basically the soil we see around us. Just quickly to complete the slide, I have put the definitions of different types of rock, but anyway, that's not important. The message I'm trying to convey here is basically different types of rock disintegrates and form sediments. Now let's have a closer look at the process of weathering. Weathering basically is the process of breaking down of rocks into smaller pieces. There are some pictures you can see in here, and basically weathering we classify into two categories. One is mechanical weathering, and all the pictures you're seeing on the right hand side are weathered by different mechanical agents such as temperature. This is an example what temperature can do, temperature cycle can do to a rock. Water, because of freeze-thaw action, if a water gets through a hole or crack into the rock, and during the night it can freeze and expand and form something like this, or break a rock, something like that. This is a picture showing erosion done by wind. Running water, you can see these pebbles when it is carried by water. These pebbles or bigger rocks will hit each other and eventually form smaller pieces. That is basically the process of mechanical weathering. Now, apart from mechanical weathering, there is another type of weathering. We call it chemical weathering. Chemical weathering is nothing but soluble salts or other chemicals in the ground or wherever. When it eats into the rock and disintegrates it into smaller particles, we call the process to be chemical weathering. Now, weathering turned in big rocks into smaller pieces. Now, what happens after weathering? Basically, two things. One of these two things might happen. Either the rock will stay at its source. We then call it a residual soil, which is reasonably uncommon, or it can get transported by gravity or wind or water or any other force and form transported soil. Now, for residual soil obviously, since it is staying at its place after disintegration, it will be developing in the areas of stable topography. On the other hand, if we look at transported soil, it will be happening in the areas of unstable topography, like these on a slope of a hill or a mountain, and then the soil thickness or the chemistry of soil in here and the bedrock may not have any resemblance. If I go back to the residual soil, so the chemistry of this soil or chemical composition of this soil, and that is the parent rock, should be not exactly the same but quite close, but for a transported soil their chemistry can be different. Now, depending on the transporting media or where they're deposited, the transported soil can be classified into different categories: alluvial, estuarine, marine deposit, aeolian deposit, and glacial deposit. These names are all new, I believe, to you. We'll be going one by one through them and try to understand a bit better what those names means. The first category is alluvial soil. It is by nothing but a fancy name given to soil formed by particles transported by water and deposited in lakes or floodplains and so forth. It has some subcategories: fluvial, pluvial, and lacustrine. You don't have to remember all these names, but you should know there are some subcategories as well. Estuarine deposit, when the soil gets carried and deposited into river estuaries, that is close to the sea, we call it estuarine deposit. And marine deposit, when the water carrying the silt or other soil particles enters the sea and gets deposited, we call it marine deposit. Now, why we are talking about these? When a river is in the mountainous area, usually it has a much higher velocity of water. That basically means it can carry much bigger particles with it. As the river goes closer to the sea, it becomes much wider. As you can see here, it's about that wide there. It's much wider close to the sea. That means the velocity of the water is dropping. Now, what does that mean? As the velocity is dropping, the water is losing its ability to carry bigger particles. Now, if I look at the riverbed in here, let's put 1, 2, 3. What do you think? The deposited soil, would it be different or the same? Obviously different. If I look at the riverbed in here, you'll be finding much bigger, coarser particles. If I'm looking here in the sea, where the velocity of water is even lower, I'll be only seeing very fine particles. And that particle size often dictates the behavior or affects the behavior of a soil as well. Here is a diagram just summarizing what I have just talked about. In the mountain, you'll be seeing much bigger particles, boulders or cobbles. In river valleys, you'll be probably seeing gravel or sand. And as we go close to the ocean or sea or a lake where the river ends, we'll be seeing silts and clay-sized particles. Now, there are a couple of other categories. Aeolian is nothing but soil deposits transported by air, and a glacial deposit, which looks like this, transported or pushed by glacier. And if you look at the figure or picture closely here, you'll see big boulders, rocks, and probably some clay deposit, all being transported by glacier, because glacier it has enormous energy and it doesn't differentiate between big particles or small particles. On the other hand, wind or water, it depends on its velocity. Now, in summary, what we have learned today, we have learned what is the engineering definition of soil, how it is formed, and different types of weathering process, different types of transporting media, and also how different particle size, or how the soil can be of different particle size depending on how it is transported. I'll leave it here. Here is some image notes, the sources of images that have been used in this lecture. In the next topic, or next video, we'll be learning about how we classify the soil. Thank you.